What if a single day, 35 million years ago, forever changed the shape of North Carolina's coastline, and we're only discovering the devastating evidence now? Scientists have just uncovered what might be one of the most dramatic geological stories ever told along the American East Coast. Deep within the rolling landscape of North Carolina's Sandhills region, researchers have identified something extraordinary, a perfectly preserved record of the moment when an object from outer space slammed into Earth and unleashed a catastrophic tsunami that reshaped an entire region. This isn't just another abstract geological discovery buried in academic journals. The evidence sits right there in Moore County, where anyone can potentially visit and witness the aftermath of an ancient cosmic collision that would have made modern natural disasters look like gentle summer storms. But here's where it gets controversial. Could impacts like this happen again? And are we prepared for the consequences? The revolutionary discovery that's rewriting regional history. Dr. G. Robert Ganis, a consulting geologist working in Southern Pines, North Carolina, has identified something that most people would walk right past without a second thought. Within a shallow channel carved into ancient Eocene sediments, his team discovered a remarkable 3-foot-thick sequence of rock layers that tells the complete story of an extraterrestrial impact and its immediate aftermath. These layers, which the research team has officially designated as the Mount Helicon Formation, represent a geological time capsule from the late Eocene period. Each layer captures a different phase of what must have been an absolutely terrifying sequence of events that unfolded over just hours or days. Think about this for a moment. We're looking at evidence of the exact moment when a fast-moving meteor or comet, known scientifically as a bolide, struck our planet with unimaginable force. The precision with which these layers recorded each phase of the disaster is nothing short of remarkable. Decoding the 4 layers of catastrophe, the Paint Hill location reveals 4 distinct beds stacked in chronological order, each one representing a different stage of the cosmic catastrophe. Understanding these layers is like reading a geological diary entry from one of Earth's most violent days. The bottom layer, designated as Bed 1, spans approximately 17 inches of dark sandy clay material. What makes this layer extraordinary is its composition. It's packed with carbon glass fragments and rock debris, but most significantly, it contains iridium concentrations measuring between 14 and 18 parts per billion. For perspective, typical crustal rocks contain virtually no iridium, making this concentration a smoking gun for extraterrestrial origin. Bed 2, measuring roughly 3.5 inches thick, consists of fine silt embedded with small Worsley-bound pellets alongside iridium levels of 2 to 6 parts per billion. These pellets appear to be accretionary lacullae, fascinating structures that form when ash and microscopic particles cluster together while suspended in moisture-laden air. The third bed presents a chaotic 2.4-inch layer of breccia, essentially a jumbled mixture of torn-up soil and seafloor fragments that still retains 1 to 2 parts per billion of iridium. Finally, Bed 4 consists of about 6 inches of coarse sand, likely deposited by a secondary tsunami wave that followed the initial surge. And this is the part most people miss. Each of these layers formed within hours of each other, capturing a catastrophic event in real-time geological terms. The Chesapeake Connection, a regional disaster unfolds. Here's where the story becomes even more intriguing and potentially controversial. The Paint Hill site sits approximately 235 miles southwest of what's known as the Chesapeake Bay impact structure, a buried crater that represents the largest known impact site in the United States and ranks as the 7th largest confirmed impact crater on our entire planet. The U.S. Geological Survey has documented this massive buried crater, but connecting it directly to the North Carolina evidence represents a significant leap in understanding the true scope of this ancient disaster. If the researchers are correct, we're not talking about a localized event, but rather a regional catastrophe that affected hundreds of miles of the eastern seaboard. Consider the implications. An impact powerful enough to launch debris and trigger tsunamis across such vast distances would have created environmental chaos extending far beyond what we previously imagined. This raises uncomfortable questions about our current level of preparedness for similar future events. The smoking gun. Why iridium changes everything. Iridium serves as perhaps the most compelling evidence for the extraterrestrial origin of these deposits. This rare metal exists in minute quantities within Earth's crust, but occurs in much higher concentrations in meteorites and asteroids. When scientists find iridium spikes in geological layers, it typically indicates either massive volcanic activity or asteroid impact. The most famous example of iridium evidence comes from the Chicxulub impact event that occurred approximately 66 million years ago. A 2021 study directly linked iridium layers from this impact to the Cretaceous-Paleogene mass extinction boundary found in locations worldwide. The Paint Hill discovery adds North Carolina to the growing list of sites where cosmic impacts have left their distinctive chemical signatures.
But here's a thought-provoking question. If iridium signatures can persist in rock layers for millions of years, what other impact events might we be missing simply because we haven't looked in the right places? Shocked quartz and the physics of cosmic violence. Beyond iridium, geologists look for another distinctive impact indicator: shocked quartz. These are quartz grains that have been subjected to pressures so extreme that their internal crystal structure becomes permanently deformed in ways that only occur during asteroid impacts or nuclear explosions. Researchers have documented shocked quartz grains from upper Eocene deposits in east-central Georgia, strengthening the regional picture of how impact ejecta spread across the southeastern United States. The presence of shocked quartz in multiple locations suggests that the Chesapeake Bay impact was indeed powerful enough to distribute debris across several states.
This evidence challenges us to reconsider how we think about regional geological history. Rather than viewing each state's geological record in isolation, we need to understand that major impact events can create signatures across entire regions simultaneously. Reading the tsunami's destructive path bed 3 at Paint Hill tells perhaps the most dramatic part of the story. The moment when ocean waters, displaced by the distant impact, came roaring inland with devastating force. This layer contains a chaotic mixture of both marine and terrestrial fragments, including fossil-bearing chert, chunks of older rock formations, petrified wood pieces, and fragments of paleosol, ancient hardened soil. The diversity of materials in this layer paints a vivid picture of the tsunami's destructive power. As the massive wave surge bulldozed its way inland from the sea, it ripped up everything in its path. Seafloor sediments, coastal vegetation, soil layers, and even chunks of solid rock formations that had been stable for millions of years. Imagine the scene, a wall of water carrying this mixture of debris, moving with enough force to transport house-sized blocks of rock and deposit them miles inland. The fact that both marine and terrestrial materials ended up mixed together in the same layer demonstrates the incredible violence and reach of this ancient tsunami. The skyborne pellets, evidence of atmospheric chaos. One of the most fascinating aspects of the Paint Hill discovery lies in Bed 2's small, loosely bound pellets. These structures, which resemble accretionary lapilli, provide direct evidence of what was happening in the atmosphere immediately after the impact. When a large asteroid or comet strikes Earth, it launches enormous quantities of pulverized rock, vaporized target material, and superheated gases high into the atmosphere. In the humid air conditions that existed during the late Eocene, fine particles began sticking together as they fell back to Earth, creating the pellet-like structures found in the Paint Hill deposits. As M.S. Huber from the University of Vienna noted in 2017 research, meteorite impact-generated accretionary lapilli remain poorly understood compared to their volcanic counterparts. The Paint Hill particles represent valuable real-world examples that help fill significant gaps in our understanding of impact processes. But here's what makes this controversial. If atmospheric conditions were humid enough 35 million years ago to create these pellets, what does that tell us about climate patterns during the Eocene period, and how might similar impacts affect our current climate system?
timing the catastrophe from seconds to hours.
The sequential nature of the Paint Hill beds allows scientists to reconstruct the precise timing of events following the impact. Bed 1 represents the first few minutes after impact, when the finest ejecta materials and carbon-rich debris began settling out of the atmosphere into the channel. The high iridium concentration in this basal layer confirms its role as the primary fallout zone, where the heaviest concentrations of extraterrestrial material accumulated first. This aligns perfectly with our understanding of how impacts distribute siderophile metals, metals that prefer to bond with iron across the surrounding landscape. Bed 2 captures the continued atmospheric fallout as the impact plume gradually thinned and dispersed. The accretionary lapilli fell like hail, indicating that the air remained humid enough to promote particle clumping even as the immediate crisis began to subside. Then came the water. Bed 3 records the moment when the displaced ocean waters finally reached this inland location, creating a churning slurry of seawater and sediment that tore up soil blocks from nearby uplands and deposited them as the surge began to lose momentum. Finally, Bed 4 likely represents either a secondary tsunami pulse or the backwash as waters eventually retreated, leaving behind clean sand and small gravel in distinctive swirled patterns that match the stop-and-start behavior of oscillating tsunami flows. The land before impact, a peaceful Eocene world, the Paint Hill deposits sit atop an older sequence that the research team has named the Paint Hill Formation. These underlying rocks contain marine fossils and show repeated cycles of fine and coarse sediments, indicating that this area experienced normal, gradual changes in shoreline position during the Upper Eocene period. Crucially, soil layers at the top of this older sequence had sufficient time to harden into paleosol before the impact occurred. This is why chunks of this hardened ancient soil ended up incorporated into Bed 3's chaotic mixture. The presence of these paleosol fragments tells us that the North Carolina coast was dry land by late Eocene time, making the tsunami surge all the more devastating as it bulldozed across an established terrestrial landscape. This detail helps us understand that the impact didn't just affect marine environments, but also permanently altered well-established terrestrial ecosystems that had been stable for potentially thousands of years. Why this discovery matters beyond academia. The Paint Hill sequence provides the first direct evidence that effects from the Chesapeake Bay impact extended deep into the Carolina region. This finding has immediate practical applications for understanding regional geological history and improving geological maps across the southeastern United States. By formally naming the Mount Helicon Formation, geologists now have standardized terminology for discussing this specific impact and tsunami deposit package. This common language will facilitate better correlation of Eocene rock sections across the entire region and help identify similar deposits that may exist at comparable elevations to the east and south. But the implications extend far beyond academic geology. Understanding how past impacts affected regional geography helps scientists model what might happen if similar events occurred today. Given that the eastern seaboard now hosts millions of people and critical infrastructure, the stakes for understanding impact-generated tsunamis have never been higher.
And this is the part most people miss. We're not just studying ancient history. We're potentially looking at a preview of future catastrophes. The convergent evidence. When multiple lines point to truth. Impact science relies on multiple independent lines of evidence converging on the same conclusion. At Paint Hill, researchers have identified anomalous iridium concentrations, impact-style accretionary lapilli, tsunami-characteristic breccia deposits, and a sandy cap layer, all arranged in a logical sequence that matches both the physics of impact events and the regional geological context. Each piece of evidence answers different questions about timing and process. The iridium proves extraterrestrial origin. The lapilli demonstrate atmospheric processes. The breccia records tsunami dynamics. And the sandy cap shows how the system eventually returned to more normal conditions.
Together, these features transform what appears to be an ordinary sandhill slope into one of the clearest places on Earth where we can literally read the geological record of the day when an object from space permanently changed the Atlantic coast. The controversial questions we must ask. This discovery raises uncomfortable questions that extend far beyond geological curiosity. If an impact 235 miles away could generate tsunamis powerful enough to reach inland North Carolina, what would happen if a similar event occurred closer to our current population centers? Moreover, if we're only now discovering evidence of this relatively recent impact event, how many other significant cosmic collisions have we missed in the geological record? Are we systematically underestimating the frequency and impact of these events?
Perhaps most controversially, given that the Chesapeake Bay impact ranks as only the 7th largest known crater on Earth, what kind of regional devastation might result from an impact by a truly large asteroid or comet? These aren't abstract academic questions. NASA and other space agencies actively monitor potentially hazardous asteroids, but our preparations for impact-generated tsunamis remain limited compared to our tsunami warning systems for earthquake-generated waves. The Paint Hill discovery forces us to confront an uncomfortable truth. Cosmic impacts have repeatedly reshaped our planet's surface and dramatically altered regional ecosystems throughout Earth's history. The question isn't whether similar events will occur in the future, it's when, and whether we'll be prepared. What do you think? Are we taking the threat of cosmic impacts seriously enough? Or are we focusing too much on statistically unlikely events while ignoring more probable dangers? Should discoveries like Paint Hill change how we prioritize disaster preparedness? Or do other threats deserve more immediate attention? The evidence is now literally written in stone across the North Carolina landscape. How we choose to interpret its implications for our future might determine whether we're prepared for the next time our planet has a very bad day.